So we have this one as a basis. E to the x and e to the x is both the function and its derivative. So if we were to look at a to the x, now what is the derivative of that? Now it should kind of follow the form, but we don't really have a lot to work with here. So what I'm going to use is the differential notation, and I'm going to make a substitute for a. So remember that from the definition of the inverse, x equals e to the natural log of x, right? That's that one identity that we had before that basically is the function and its inverse. So if instead of x, I use a to the x, what I have here is a to the x on the left side, and so on the right side it's e to the ln of a to the x. So you see how I made that substitution there. And so if I use the properties of the natural log and bring that out to that x in front of the natural log of a, what I can do now is use the chain rule to take the derivative. First, I keep the original function, and then I'm going to take the derivative of x ln a. That's an easy derivative because ln a is a constant, so it's just going to be ln a. Okay. And then there's one more step that I'm going to take. Remember I had this e to the x ln a, that is what we started with here. And I can put that back into the a to the x form. And so the derivative of a to the x is a to the x times the natural log of a. Okay? So you may not have followed all that. I would suggest that you go through it just to become familiar with taking derivatives with the substitute like that. But this is the thing that you got to remember. That if we have the function a to the x, the derivative is a to the x times the natural log of a. And remember, the natural log of a is a constant. So if we do anything more with it, we treat it as a constant. Yes?
So why can we substitute a to the x with e to the ln, or e to the natural log of a to the x? Why can you substitute it?
Why can't I?
Why can you?
Why can you like this?
Yeah.
That's just a universal substitute. So if I have a to the x, that will be e to the natural log of a to the x. That's just this whole thing up here. That's the same thing as saying x equals e to the natural log of x.
And
like
then
that.
when you say it's a natural substitute, does that mean that you can use it for other?
Well, if you did it with other bases, you'd end up with this. Like if you use base 10, then you would have a to the x equals the 10 to the common log of x. Now taking the derivative of this is a problem because we didn't make it any simpler because we still don't know the derivative of 10 to the whatever. We're trying to do bases other than e. And I use e because I know the derivative of that. Okay, so now we have derivatives for any exponential function, right? Okay, so let's look at log functions now. Let's say we have f at x equals the natural log of x. Y is the natural log of x. It's just rewriting that. And I'm going to rewrite it as e to the y equals x. This is just a rearrangement. There's nothing tricky or underhanded about that. I'm just restating what the log is. Now, if I want to take the derivative of this, remember implicit differentiation? That's where I take the derivative with respect to x in a statement that includes y. So the derivative of e to the y is going to be e to the y, and then by chain rule, y prime, right? And then the derivative of x is 1. So I have this by implicit differentiation. And so I have y prime equals 1 over e to the y. That isn't what I was looking for, though, really. I want an expression in x with the derivative. So I look back and I see e to the y equals x, so this is just x. So here's a nice, tidy, remarkable derivative in its own right. The derivative of the natural log of x is 1 over x. Okay? So again, like e to the x is a simple derivative, it's e to the x. The derivative of natural log of x is a simple derivative, it's just 1 over x. Okay, so how about an arbitrary log of base that we have? What's the derivative of that? So I'm going to do kind of the same thing again. I'm going to take a to the y equals x. And then using implicit differentiation, remember when I take the derivative of a to the y, that's going to be a to the y natural log of a. Remember how the constant comes out. And then by chain rule, I'm going to take the derivative of y. Derivative of x is still 1. And so when I solve for this, I get, I have a to the y. I really want x, so I'll put x in here. And then if I take the, divide both sides by xl and a, I get the derivative of y is 1 over x to the natural log of a. All right, so here's the statement that you have to memorize. So if the function is the log base a of x, its derivative is 1 over x natural log of a. So you have that natural log of a kind of constant following you around on this one as well. Okay, so in summary, here we have our derivatives that have to do with exponential functions and logarithmic functions. Now, these two, the first two, are clearly the most important ones. The second two are important if we're going to be dealing with logs and exponential functions with bases other than e. So get used to this one, but you also have to remember these because your differentiation gateway will rely on you knowing what these are all about. Okay. So just to remind you, the derivative of e to the x is e to the x. When it's e to the u, we have to use the chain rule. So the derivative of e to the u is e to the u times du dx. So some examples, we did these last week, like if we have g at x equals e to the 3x, the derivative is going to be e to the 3x times the derivative of 3x, which is just 3. All right? And so we'll rewrite it as 3e to the 3x. So if we have a more complex function, like x squared plus x as an exponent, the derivative is going to be the same thing, and then times the derivative of the exponent. And so we can rewrite that. It's not so important that we rewrite this one, but generally you take your algebraic terms before your exponential terms. Whoops. I'll let you catch up. But this is what we did last week, so hopefully this isn't news at all. Yes?
Is this lecture already posted on Moodle?
I'm going to post it after class. I don't have the actual file up. Okay? So sorry about that. I try and get them up, but today it didn't work. Okay, so let's look at some other things. Remember, if our function is the log of x, the derivative is 1 over x. So let's say we have the log of u. We do the same thing again where we take 1 over u times du dx. So we take the derivative by chain rule again. And so a couple examples here is if we have the natural log of 2x plus 1, the derivative is going to be 1 over 2x plus 1. The important thing is to remember that it's multiplying by the derivative of u with respect to x. Don't make the mistake of putting that in the denominator. That's actually 2 times that. So when you rewrite it, it's going to be 2 over 2x plus 1. Another example, if we have that x squared plus x as the argument to the log function, the derivative is 1 over x squared plus x, and then we take that times the derivative of what's inside that inner function x squared plus x. And so rewriting that, we just get 2x plus 1 over x squared plus x. Okay, follow the pattern okay? So let's look at another thing. When we take the natural log of y by the chain rule, that's going to be 1 over y times dy dx. And so we get y prime over y. Now this is kind of an interesting thing because it's going to give us a tool to do a few more derivatives that we normally couldn't do. Like let's say we have this. You know how to do that already because you can use the chain rule, not the chain rule, the quotient rule, right? You take the derivative of this times that, minus this times the derivative of that, and then you take this squared. Watch how I do it a lot faster. I'm going to take the log of both sides. And so when I take the log of this, I can put it out into two different expressions in logs, right? The log of 2x plus 1 minus the log of x squared plus 7x. Now let me take the derivative of both sides. I know that the derivative of the log of y is y over y prime over y. The derivative of this is just going to be 1 over 2x plus 1 times the derivative of that, which is 2. The derivative of this, we retain the negative sign, it's going to be this x squared plus 7. And then the derivative of x squared plus 7 is 2x plus 7. We're looking for y prime, we're not looking for y prime over y, so we'll multiply both sides by y, and that's not nearly as problematic as it looks at first because you already have y. This is what's known as logarithmic differentiation. It's a way to do derivatives of rational functions very, very quickly, and in fact you can do them by sight with this. Let me see if I have another example, otherwise I'll make one up. Yeah, I'm going to make one up before we get to this. Let's say we have our function is going to be x plus 1 squared times x minus 1 over 3x minus 1 times 2x plus 1. That looks like a quotient rule problem from hell, right? I mean, there's a lot of things that you have to do when you take the derivatives of the numerator and the denominator. You're going to have a quotient rule or the product rule going in. So instead what I'm going to do is I'm going to first take the log of both sides. So I'm going to call this y. So I get the natural log of y equals, and I'm going to right away visually split this up. I know the numerator terms are going to be 2 ln x plus 1 plus ln x minus 1 minus ln 3x minus 1 minus ln 2x plus 1. And so if I take the derivative of this, I know that's y prime over y. Taking the derivative of this is going to be easy. 2 over x plus 1 plus 1 over x minus 1 minus 3x minus 1 in the denominator, and by chain rule, it's 3 in the numerator, minus, and then we have 2x plus 1, and by chain rule I have 2 in the numerator, and then I'm going to multiply it by my original y, which is x plus 1 squared, x minus 1, 3x minus 1, 2x plus 1, over or times all these terms. 2 over x plus 1 plus 1 over x minus 1 minus 3 over 3x minus 1 minus 2 over 2x minus 1. Much faster than the quotient rule, right? I did this in 4 steps. And so you can actually, if you visualize what's going on here, I'm starting with my original function, and then I'm just taking these things and taking the reciprocals and using the exponents as the coefficients. I'm getting, you know, you can almost do the derivative of this in your head, you know, if you're well practiced enough. But this is a much more straightforward way to take derivatives when the quotient rule just looks like it'll be a bear. Okay? All right, so let's return to this. We want to find f prime if f at x equals x to the x power. So what do we use here? Do we use the rules for exponents, or do we use the rules for the power rule? Like if we have x squared, that's going to be 2x. Well, that's not going to work if we have a variable both as the base and both in the base and the exponent. So the thing that we'll do here is let's take the log of both sides, because what the log will be able to do for us is that we can take that x as an exponent, make it a coefficient in front of that log of x. Okay, now we have something we can take the derivative of. So remember, the derivative of y is going to be y prime over y. The derivative of this is just going to be the product rule. Derivative of x is 1 times the log of x plus x times the derivative of the log of x, which is 1 over x. And so what we get, when I simplify this is 1, this is the log of x. We multiply both sides by y, and then we substitute back in what y is, and so here's our derivative. X to the x times ln x plus 1. Now, you got to be careful with these. If this is, you know, a 2x in here, then we got to treat the 2x properly all the way through it. So there's a trap sometimes in just thinking that we'll, you know, retain a coefficient, which you do, but remember that you have to take the derivatives properly, especially when you are taking the log of both sides, that you take out the proper coefficient. Okay. So here's a few for you to try. Try these derivatives and see what you can get from it. Okay, these all involve the derivative of the natural log, which is 1 over u times u prime. So you have to take the reciprocal and then multiply, chain rule, multiply the derivative because of the chain rule. So let's look at the first one. Excuse me, I think I'm getting a cold. So we look at the derivative as 1 over 5x plus 1, and then times the derivative of 5x plus 1 by chain rule, and then we can make it 5 over 5x plus 1. I hope you're not writing equals and then the derivative. Make sure your notation is complete and accurate, that you're starting out by writing what you're doing, which is the derivative. The derivative certainly doesn't equal the main function. Okay, so there's a couple ways to do this next one. The easiest way is just to rewrite the function to have the coefficient, have that exponent now the coefficient of the natural log. And so when we take the derivative of it, we just have 2 over x. Now we could do it by keeping it all intact, if it just doesn't occur to you to do anything different. So the derivative of this then is going to be 1 over x squared times the derivative of x squared, which is 2x. And so you can see 2x over x squared is going to be 2 over x. So you get to the same place, but it's just simpler if you remove all the exponents first. So this last one's a little bit bigger, a little bit more complicated. So we'll take our derivative, or actually, what we can do here to avoid ultimately doing the product rule in here is we'll separate this out into two statements where we have the natural log of x plus the natural log of e to the x. Now this is really, this is the inverse of a function, and so the natural log of e to the x is going to be equal to x, and so our function really just amounts to the log of x plus x. And so taking the derivative of that then is 1 over x plus 1. And we can do it the long way if you want, but you know, there you're going to have a bit of simplification to go through, and it's just easier as a rule for taking any derivative is first simplify the function as much as you can. And with logarithms, that often means break up the factors so you get, so now you get a bunch of derivatives that are sums rather than products. Okay, here's a few more. Okay, find the derivatives of those two. So for the derivative, just make sure that you have the natural log properly placed. So you have 1 over 3x plus 1 times natural log. And then by chain rule, the 3x plus 1, the derivative is just 3. So when we write that as a simple ratio, we just have 3 over 3x plus 1 natural log of 10. Now this next one is logarithmic differentiation, and remember the pattern of that is that we can take the log of both sides, and so the right side disassembles into all those different terms, the sums and the differences, and then we take the derivative, we get y prime over y, and so these are easy derivatives. This is just 1 over 1 plus x, 1 over x minus 5, and then we have negative 1 over x plus 2, and this is going to be 1 over 2x minus 3, and then by chain rule, we have a factor of 2, and then we're going to multiply back our original function, and so what we get is the original function times all those reciprocal terms that we got out of the logarithm. And like I said, if you remember the pattern, you can go directly to this. You just copy over the function, and then we just take the reciprocals of each of these terms. The terms that are in the denominator get a negative coefficient, and then just remember if we have a chain rule to do that, we take the derivative of 2x minus 3 to put the 2 in the numerator there. Yes?
Is there an easy way to simplify all that, or can we just leave it
You
like
can
that?
simplify it now. You can make a common denominator, and you'll get the mess that you get if you did this with the conventional quotient rule.
Okay,
If you're actually computing this, this is the way to go. Leave it like that, okay? Certainly in this class, you don't have to simplify that. I mean, just think about it. If you have the value of x, would you just plug in x and use those terms rather than making a common denominator and have all those numerators with all those factors in it? It's just simpler from a computation standpoint to do. Yes?
I get the multiplying by 2.
This one here by 2? Because the derivative of the natural log of 2x minus 3 is 1 over 2x minus 3, and then by the chain rule, we have to multiply by the derivative of the 2x minus 3, which is 2. Here, the chain rule says that the derivative of x plus 2 is 1, so there's nothing that comes out of it. But that's what you have to do, is whenever you take the derivative of a log, or any function for that matter, it's going to operate on that function, but then you also have to multiply by the derivative of the function because of the chain rule.
Right, so you just didn't write the times 1 times 1. Okay.
Mm-hmm.